Welcome back to Chapter 20. We're finishing it off today with Section D, related rates. In a related rates problem, we will have two quantities which are related to each other through an equation or a formula. Sometimes that formula will be given in the problem. Sometimes it will be something that we need to come up with ourselves. And those two quantities will be changing, and we will be interested in their rates of change, hence the name related rates. And you can see now how this plays into differential calculus. Since we're finding an instantaneous rate of change, we're going to have to take some derivatives. The basic strategy here is if we can get a diagram going, we're going to want to have that, but it's not always necessary. Sometimes you'll be able to mentally figure out what kind of equation you're going to need to come up with. We're going to need to know the difference between what's a variable and what's a constant. Sometimes we'll have a constant even if we don't know what its value is. And then whatever the problem calls for is going to be the equation that we'll write down. Oftentimes, it will have to do with Pythagoras theorem, lots of similar triangles, trig, stuff like that is very common within these problems. We're going to differentiate the whole equation, and then we're going to solve some stuff. Check this right here. We're differentiating with respect to t in all cases. We're going to have two variables which are changing with respect to time. So even if we have an x somewhere in our equation, that's not the variable of differentiation. T is going to be. That's going to give us something called a differential equation, which, hey, this is like super important later on in the course, like when we get to option calculus. For us right now, it's an equation that has a derivative in it someplace. So don't worry about that. Word of warning down at the bottom, don't substitute in values before you differentiate. That's a quick way to get everything totally wrong. Now the classic related rates problem is the sliding ladder problem. We got a ladder leaning up against the side of the building. The bottom of the ladder starts sliding away from the building. The top of the ladder starts sliding down the side of the building. How do their rates travel? Well, I don't have a ladder to videotape, but I can demo this really quickly with two calculus textbooks. And what's potentially interesting is that the top of the textbook and the bottom of the textbook, they travel at different velocities. So here's a problem that we can do. All right, we got the ladder, we got the wall. This is amazing. We're told that it's slipping away, and when the bottom of the ladder happens to be 3 meters from the wall, the bottom of the ladder is moving at 10 meters per second. How fast is the other end moving? Okay, let's get a picture going. So here we got AB is the ladder, BO is the wall, AO is the ground. Cool. We know that the ladder itself is 5 meters long. The relationship that we can establish from this picture is x squared plus y squared equals 25. We're going to differentiate now. When we differentiate with respect to t, so we got to use implicit differentiation, we're going to get 2x, but then dx dt, and then 2y dy dt equals to 0, right? Because derivative of a constant is going to be 0. And we can then divide everything by 2 to get x dx dt plus y dy dt equals 0. If it's me writing this down, I'm writing x prime plus y prime because it's less writing. It is at this moment that we can substitute in our specific values. So we know that the horizontal distance, which is x, is going to be 3. We also know that dx dt, that rate of change, is going to be 10. And because of that, because I know that this distance is 3 and this distance is 5, I can then work out what the vertical distance is, again, using Pythagoras. Whoops. So that tells me that the height's going to be 4. And now I have this is a very easy equation to solve, right? We're just solving for dy dt, and it ends up being negative 7.5. That's it. It's a negative velocity because that the height is decreasing over time. It's getting closer to the ground. Notice that if we tried substituting in the values before we differentiated, then this would have all come out to be crap because we would have had a constant over here plus y squared equals another constant, and then we would have lost all the x terms. So that makes the problem totally impossible to do. So that's what you really got to be careful of. Now this problem here is truthfully very simple. Like I said, this is the classic example. We'll look at some, I think, much more challenging ones in just a second. But I want to point out one thing that's kind of curious here. If we take this step right here and just rearrange some things, right, we get this equation right here. Now, what this means is that as the top of the ladder gets closer to the ground, the velocity should be increasing, right? Or the speed should be increasing. Let me say that. The velocity is increasing in the negative direction, whatever. Which makes sense, right? Because like gravity, it's going to have the velocity getting like faster and faster as it's pulled down. But as the height gets closer and closer to being 0, our y prime ends up getting closer to negative infinity. And clearly that's not true. So what exactly is going on here? Well, it turns out as that ladder starts to fall, at some point, the top of the ladder is no longer in contact with the house. It actually separates from it. And from that point onward, our model is no longer valid because we no longer have a right triangle. But as they say, no model is perfect, but some models are useful. So this equation does do a very good job at getting us an answer that we need, as long as we ignore, lots of things about physics like friction and air resistance and almost every other physical constant. Anyway, let's just move on and do some other related rates problems. Okay, let's do this thing, and I'm going to intentionally do this kind of thinking out loud, maybe not doing things the most efficient way at first, because I want you to see the different things you're going to need to think about as you go through a problem like this. So this is clearly more challenging than the ladder. So first of all, a cone is also a pretty common geometrical construction for related rates, because a cone comes with similar triangles built into it. And that's the first thing we need to know to exploit. So if we were to label, say this, we have it labeled here. This is the height of our amount of water that's still in the cone, and this is the radius at that particular time, but the entire cone has a height of 0.45 and a radius of 0.15. From this, we could establish two different equations. Well, really one equation written two different ways. I'm going to write them both down. We could say that r is equal to h over 3, or we might rewrite that as h is equal to 3r. Only one of those is going to be helpful in this case, but it's not always obvious maybe which one we want to use. The thing that's going to be our key here is to figure out what are we being asked to solve for in the end. Well, they want dh dt. So that means that I'm going to want to eventually have an h in my formula, which means I'm going to be replacing r. So this is the one we're going to end up using in a minute. But if that was too much all at once, just write them both down, and that way you've got them both. And we'll come back and we'll be clever about this in just a moment. Let's start writing down some stuff that's going on here. So we've got a volume of water, and it is a cone. They give us in this problem that the volume of a cone is equal to pi r squared h over 3. Using the substitutions above, we could rewrite that in two different ways, right? It could be pi h cubed over 27, or it could just be pi r cubed. Whatever. If it helps you to just see them both for right now, because you're afraid of going the wrong path here, great, whatever. Write them both down. No problem. This volume's changing. It's changing over time. So I could write dv dt, but I'm lazy, so I'm just going to write r prime. And then I'm going to differentiate. I'm not going to bother working with this part. I'm going to just work with the other two. The first one, The 3 would come down, 3 over 27, that's going to give me pi h squared over 9 times h prime. But that's also the same thing as 3 pi r squared r prime. Again, I'm just writing them both down as if I didn't know which one I was going to use, even though the one I'm going to use is on the left. Now, what do we do now? We go back and we start reading a little bit. So in this problem, it says that so the water's flowing out through the holes at this rate of Ka meters cubed per minute. Well, the water that flows out through the holes that's how the volume is changing, right? That is our V prime. So this whole thing, pun, this whole thing should be equal to Ka. And they tell us that K is equal to 0.25, and they give us this expression here for what A is. So we can jot that down. At this point, I'm just going to write down the formula that we'll be using, although, again, I might not have figured this out at this point if I was working this out. So, okay, so I've got this, and that's going to be equal to, we've got 0.25 times A, and A is going to be pi r square root h squared plus r squared. Now, in the problem, they mentioned just Ka as though it was a positive quantity. Because I'm considering the volume of the water in the cone, I'm going to throw a negative in front of that. I could just interpret this value as a negative rate of change in the end, but I like throwing a negative in the work, so when I solve for h prime, I'm going to get a negative number. Of course, if I was discussing if this is some weird situation where water was flowing into the cone through the same mechanism, then this would be a positive rate of change. These are the type of things we need to be aware of and to consider, though, when we're dealing with rates of change problems. Are the rates changing positively or negatively? Okay, so then what else do you know? Oh, they tell us that h is equal to 0.3, and then using our substitution formulas from earlier, that tells me that r is going to be equal to 0.1. And now I'm good to go, because now I can take both of those numbers and substitute them in that bottom row for h and for r. And then we're just solving for h prime. From there, the problem's easy. We're going to get the h prime should be equal to, well, it'll be a negative 0.791, a whole bunch of other crap after that. But that's all. I mean, like once you get into it, once we get to here, it's actually very simple. We just need to substitute values in. But certainly there was like this paragraph up in the top left of the screen. That's very intimidating. Even this picture. Oh my! It's two cones in one, and oh the water coming out of the cone. It's in 3D. What do we do? It's fine. It's fine, but it's clearly a little bit more complicated than the latter. Let's do one more. And then this thing. I mean, what the hell is this? What is this? It's going to be okay. Let's just do some geometry. It'll be fine. Okay, so we've got another tank being, in this case, the tank's being filled. The last one is being emptied. It's a cylinder this time. And our expression for volume, it's not a volume with respect to time in this case. It's actually a volume that is dependent upon what the height is. So we have v of h rather than v of t. So when we take derivatives, in this case it's actually going to be d whatever dh rather than dt. So what do we do here? Well, let's start off by just noting that our volume at a particular height, so v of h, that's got to be equal to the length multiplied by what I'm going to call a of h, which is just the area of the segment of the circle. So this region right there that's colored in whatever, orangish brown or something. I'm colorblind. I have no idea what color that is, but it's not important. Um, and that's true because the amount of this cylinder, which is filled with oil, is a prism with two congruent bases, one here and one over here. So its volume is equal to its height, which is L, multiplied by the area of one of its bases. So we've got that. And now what is A of H? So A of H is equal to, it's going to be the area of, as I said, of that segment of the circle, and we can calculate that by taking the area of the entire sector of the circle and then subtract away the area of the triangle, which if we call the central angle of the circle equal to theta, and then just using area of a sector and the trig area of a triangle formula from our data booklet, we get this expression here. Now, it's starting to look like this expression for V of H that we're supposed to find. We've got L times some stuff, and that stuff does have a difference happening in it, and we even got like an r squared in the first term, so that's cool. But now we need to justify that the rest of these expressions are equal, and we're going to do that by taking a look at this triangle here. So if we drop down an altitude and just look at half of that triangle. So the angle is going to be theta over 2. We've got a hypotenuse that we know is going to be r. This height is going to be r minus h, right? Because we're taking the whole radius here, but we're subtracting away this part, which is equal to h. And then it'll be relevant in a minute, so we can use the Pythagorean theorem to figure out the second leg is that. And just glancing back at what we're going to hopefully show in a second, I see an r minus h. I see a square root of 2hr minus h squared, so that's all very promising. Since we've got an angle here, let's work out what's the cosine of that angle, and in fact, what's the sine of that angle. Why am I doing those two? That's because right here I've got an expression with sine, and right here I know cosine has to come into play somehow. So that would be what would prompt me to do this. Okay, so I've got a cosine and a sine. I can solve for theta over 2 using the red expression for cosine. Theta over 2 is equal to inverse cosine of r minus h over r, which is of course the same thing as 1 minus h over r. Therefore, this expression is the same as this expression. The r squareds are the same, and then this theta over 2 here is equal to inverse cos of 1 minus h over r. So that part's done. Now for the other part, I've got to somehow get this blue work to give me this product. And we can do that by working out what the sine of theta is. Now theta is of course twice theta over 2, so I can use my double angle formula. I can then substitute in the values for sine of theta over 2 and cosine of theta over 2. And then check this out, right? We've got this r squared and this 2. So we can move those over to the left-hand side here, and we've got r squared sine of theta over 2 is equal to all of that. And that's exactly what we needed to show. So part A is finally done. Part B, I promise, will not be any more pleasant. So now we got to take the derivative of this thing. Now, when we do this, I want us to remember that in this problem, r is a constant. H is a variable. Right? R, the radius of this cylinder is never changing, only the height of the oil. So when I start taking derivatives here, R is a constant. All right, hopefully everything's going to simplify to this expression. Let's see what we can do. So for starters, L is also a constant, right? Because that's the length of the cylinder. So V of H is equal to L times all this. Since that's a constant, I know that my V prime is going to have an L times some other stuff. Now we take the derivative of what's inside. Once again, R squared is a constant. So it'll be R squared times the derivative of inverse cosine of 1 minus H over R. So if we get out our formula books, we can be reminded that the derivative of inverse cosine of x is equal to negative 1 over the square root of 1 minus x squared. We're going to use that here. Instead of x, though, we're going to have to use the chain rule. Instead of x, we've got 1 minus h over r. Whew. So this is r squared times this. So let me write negative r squared over the square root of 1 minus h over r squared. Then we chain rule and we multiply by the derivative of 1 minus h over r. The derivative of 1 is just 0, and then the derivative of minus h over r is just going to be minus 1 over r. And we'll simplify those two expressions together in just a moment, but that's the derivative of our first term, minus. Our second term, we could either choose to distribute or we could view this as a product. That's how I'll do it. It's r minus h times that square root. So the derivative of r minus h, for starters, is just going to be minus 1. So it's minus 1 times the square root. And then we're going to add to that r minus h times the derivative of the square root, and take the derivative of the square root. That's going to give us 1/2 times the stuff that's in the square root to the negative 1/2, and the chain rule again. The derivative of 2hr is just going to be 2r. And then we subtract the derivative of h squared, which will be 2h. And, we've successfully taken the derivative. Bravo. Now we just need to simplify it. This, as you can imagine, is going to take a little while, so if you're not interested in the algebra, I guess just that's the end of the video, but let's go through it anyhow. So for starters, we've got this r squared and this r, and of course the two negatives, so we can combine all that to just get us r over that square root. I'll deal with that in just a moment. Here we're going to distribute this minus, and I've got plus this term, and then minus all this other stuff. Now I've got a 2 that I can factor out here, which will cancel with the 1/2. And then I've got an r minus h and another r minus h. So that's r minus h squared divided by, again, that square root, since I had a negative 1/2 as an exponent. Then working with just this first term, so the other stuff, I'm too lazy to write it out. We'll deal with that in a moment. We're going to first square this binomial, so we've got that there, and then we're going to subtract it. So we've got this going on here, and then if we've got the square root of r squared in the denominator, so we can pull that out of the square root, and then we have r divided by 1 over r, which gives us r squared in the numerator over the square root of 2hr minus h squared, right? Because now that has a denominator of 1. And that's cool, because now that matches the denominator from our last term. The middle term stayed the same, and I expanded the r minus h squared here in the numerator. Now we're going to give everything the common denominator, which is just the square root of 2hr minus h squared. Whew. Combine all these like terms now there. This the middle term, obviously, we're going to ditch the square root since we've kind of shifted that down to the bottom. Putting everything together, we just get 4RH minus 2h squared in our numerator. This is cool. We can factor out a 2 from each of those terms. Take that way out in front. So now I've got 2L times 2HR minus h squared to the power of 1 divided by 2HR minus h squared to the power of 1/2. Combining those, and we get 2L times the square root of 2HR minus h squared. And that is what we wanted to do. They have the h factored out here. I forgot to write that down, but yes, we could factor out that h term under the square root, and we will have completed part B. And now finally, part C. Okay, so we want to find out how fast the height is increasing. Now notice here, ooh, they're telling us that the tank is being filled at 0.6 meters cubed per minute. So in the previous part, we were dealing with dVdh, and I was being a little lazy, and I was just writing v prime. And the downside of the prime notation is that it doesn't tell you what you're differentiating with respect to. You just kind of have to keep that clear in your mind. And in part B, we were differentiating with respect to height. But here, they're giving us the rate of change of volume with respect to time. So dV dt is equal to 0.6. And now I need to figure out how that relates back to part B, which was with dV dH. Now, the idea with these derivative, I don't like calling them fractions because they're not like proper fractions with numbers, but they can behave like them at times. So the truth is, dV dH, if we multiply, if you will, by dH dt, we get dV dt. And you can kind of see how you could just cancel dH's, if you will. And that's quite convenient because we have an expression for dV dH. We know that dV dt is 0.6, and we're trying to figure out what dH dt is. So all we need to do is rewrite this equation and then substitute some stuff in. So dV dH, excuse me, what am I saying? dH dt, that's going to be equal to 0.6 divided by our expression from part B. So divided by our, what is it, 2L times the square root of h times 2r minus h. And then we are told that L is equal to 10, and we're told that R is equal to 1.5, and we're told that H is equal to 0.5. So we just need to substitute all of that in, and in the end, with our calculator at our side, we get 0.0268 to 3 significant figures. Done finally. This is obviously from a textbook, but this is the kind of wild thing that, you know, if you're unlucky, that the IB could throw at you at the very end of an exam. A very long question with many parts to it. Part A was really all about geometry and knowing how to manipulate some trig identities. Part B was really the calculus part with taking derivatives and knowing how to use a bunch of different formulas, using your chain rule, followed by some algebra to finally get down to the expression as they desired it to be. And then part C was a little bit of like final algebra of whatever. It would be if it was an IB exam, part C would be a hence problem. So you'd know, like, oh, even if I couldn't figure out part B because that was a monster, I can still do part C even if I only have a few minutes left at the end of the exam, because it's really just substituting in some values, as long as you're clever enough to come up with this idea here. So that's the kind of stuff that related rates could be like. It could be something really crazy complicated like that, but it also can be something exceedingly easy. So as with everything else, the key here is going to be to practice as many different examples as you can. So we'll have some in class. I've also got an additional problem set on the class website with a whole bunch of related rates problems with solutions all worked out for you to look at in your spare time because, of course, that's definitely how you want to have fun at home with family and friends, is to do related rates problems. So yeah, I'm tired of talking. So the end.